Hello, welcome back. In this video, we're going to go over the second course learning objective, which is finding and sketching the vertical asymptotes of the graph of a function. And we're going to use the skills from the first course learning objective, which is all about finding and determining infinite limits from the left and right. So this is going to be the major input for vertical asymptotes. All right, let's hit the road. So I'm going to start with the same two examples we went over in the first video. And remember that we had f of x equals 1 over x minus 1 quantity squared and negative 1 over x minus 1. These two functions are good representative examples to talk about vertical asymptotes because in both cases, the point 1 was a problem point because that makes both functions to blow up to minus infinity or plus infinity. Like in this case, for example, if you're approaching 1 from the left, the corresponding function values approach plus infinity. And if you're approaching 1 from the right, as you see, and then the corresponding function values went down to minus infinity. Okay, so if we expand the graphs all the way to plus or minus infinity, here we go. I plotted two of them in the same plot. So you have the red and orange representing these two functions, and the dashed line is the vertical asymptote. So I plotted for the range of y in between negative 500 and 500, but as you see that if I zoom out, uh, the red and orange guys are gonna approach plus or minus infinity, but they're gonna go along the vertical line and they will never ever touch. So the graph of f will never ever touch to the vertical asymptotes, but it's gonna go to infinity or minus infinity along the vertical line. That's why we call it an asymptote. All right, so here's the skill that we learned from these two examples. In both cases, x equals 1 makes these two functions blow up to minus or plus infinity. So that brings up the definition of vertical asymptote. So your function, if the function of consideration is approaching infinity or negative infinity, as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. And notice that you're having a number divided by 0, not 0 dividing 0. So you should sort of like look for that pattern. In fact, we're going to summarize this in this result here. So if you have a rational function, which is f divided by g, and both of these functions are continuous on an open interval containing c. So if f is not 0 at c, but g is 0 at c, so you're dividing a number by 0, for that reason, x equals c is a good candidate of a vertical asymptote. So essentially, once a rational function is provided to you, all you're going to check is to look for the points that make the denominator 0, but not the numerator. So those points are the best candidates of vertical asymptotes. And here is a good example to find vertical asymptotes. So let's say like the function provided to us is 1 over 2 times x plus 1. Well, this is a rational function whose numerator is 1, which is totally non-zero, but the denominator becomes 0 at x equals negative 1. So x equals negative 1 is a good candidate of a vertical asymptote. And you can graph the function and you can observe it by yourself. But once you pinpoint a vertical asymptote, which qualifies for this case scenario, that the point that you search for makes the numerator non-zero but the denominator 0, you can go ahead and write down the two limits. One is that you're approaching that problem point from the left, and you're approaching the problem point from the right for the same function, and to see exactly what these guys approach, uh, because we have to quantify it as like plus or minus infinity. Okay, so for example, on the left of negative 1, we see that the function values tend to negative infinity, so I'm going to put negative infinity here. And on the right of negative 1, the function values get like arbitrarily large, and for that reason, this limit is plus infinity. And here's another cool example, which is again a rational function, x squared plus 1 divided by x squared minus 1. By the way, once the rational function is provided to you, if the top and the bottom are polynomials, it's better to factor the top and the bottom as much as you can so that you can actually recover, you can actually find the zeros of the denominator easier that way. And you can see also the cancellations of the factors if there are any, so that you avoid 0 over 0 type situations. So in this case, this polynomial is irreducible, so you can't factor it more, but x squared minus 1 is reducible, and it's the product of x minus 1 and x plus 1. And we can easily see that x equals minus 1 and x equals 1 makes the denominator 0, but not the numerator for sure, because at those values, the numerator x squared plus 1 is non-zero. And by looking at the graph of this function, you can easily see that x equals minus 1 and 1 are good vertical asymptotes. So to solidify that, you should look at the left and right limits at these 2 points. So you're going to, in fact, look at 4 limits. One is the limit of the function as x approaches minus 1 from the left, and the other one is x approaching minus 1 from the right. Okay, you're going to check those limits. I'm going to skip that here, but you will do it once you pause the video. And you will also check 2 more limits. One is plus 1, and the other one is plus 1. You're approaching 1 from the left, 1 from the right. So in total, you have 4 limits to check to quantify what those limits are, either like plus or minus infinity. And here is our final example in this list. It's cotangent x. It's a trig function. Cotangent x, as you may remember, it's cosine x over sine x. And you're looking for x's for which the bottom is 0, the denominator is 0, and the top is non-zero. And if you search for those values, sine in fact becomes 0 at the multiples of integer multiples of pi. So at those points, cosine is totally non-zero because it takes the value of -1 or 1. You can just try with your calculator or check the unit circle if you want to. And this tells us that we have in fact multiple vertical asymptotes at the integer multiples of pi. See, this is like x equals pi. This is x equals 2 pi vertical line. X equals negative pi. X equals negative 2 pi. So you can actually go in this direction, in the x direction, to plot more vertical asymptotes of the graph of cotangent x. All right, our final discussion is about the properties of infinite limits. Let's say like we have 2 functions f and g, and we have the point, limit point to be c. And let's say like the limit of f as x approaches c is infinity, and the limit of g function as x approaches c is just some number L. Okay, not infinity, but some number L. And we're looking at the limit of the sum or difference of 2 functions in the first case. Well, the limit of f is in fact infinity. The limit of g is a finite number L. So infinity plus L is going to take you to infinity. Okay, so that's sort of like the logic behind it. If you have 2 functions multiplied, and if you look at the limit of that, one takes you to infinity, the other one takes you to a number L. So a number times infinity is going to be plus infinity as long as L is positive. If L is negative, that number is going to be negative infinity. Okay. And you can also look at the quotient. The limit of the quotient is going to tend to 0 because this g tends to a finite number, and this f tends to infinity, which is extremely large. A finite number divided by an extremely large number is going to take you to 0. Okay, so we're going to use these properties along the way for the next example. All right, let's start with part A. We have the limit of 1 plus 1 over x squared, and we know that limit of the individual function 1 is just 1 because it's a constant function. And individually, limit of 1 over x squared as x approaches 0. That should be infinity because uh, from the left and from the right, you're dividing 1 by a very small number, which is positive, because any number you take close to 0 and square it, that's going to be a number very close to 0. So this limit is infinity. So you have a finite limit and infinite limit. So that takes you to infinity because of the first property here. Okay. And in the second example, we have the limit of a quotient, and the top is a polynomial, and at 1 from the left. This limit is going to be just direct substitution. It's a finite limit. 1 squared plus 1 equals 2. And for the quotient, we got to be careful because as you get closer to 1 from the left, so you're almost like on the left of pi, but pi is an asymptote for cotangent, and you can check it by graphing this function. Then this limit is going to be negative infinity. So the top is finite, the bottom is approaching negative infinity. So we're in the last case here, that this limit, finite divided by infinite, is going to take you all the way to 0. Okay. And in part C, we have 3 ln x, and well, we can split this again as the product of 2 limits. And limit of the constant as x approaches 0 is just that constant 3. And on the right of 0, ln approaches negative infinity. You can also graph this function ln x and see by yourself. And now we're going to apply this property here. Okay, either one of the properties, but apparently we're in the case of like negative infinity, so we're applying this property here. Okay, so the product is going to have the limit negative infinity. Okay, so that's property 2. And finally, we have the sum of x squared and 1 over x. And x squared individually approaches 0 as x approaches 0 from the left by direct substitution. And on the left of 0, 1 over x is going to blow up to negative infinity. So we are in the case of property 1. We have the sum of these two functions. And since one of the limits is negative infinity, the sum is going to be dominated by that. So this limit is going to be negative infinity. All right, I think that's all it is. So we have just finished the learning objective, the second learning objective of this section. And please go ahead and start the recitation videos and practice this content to the full extent. All right, thanks for watching. I'll see you in another video. Bye.